thanks to the organizers for setting up this really nice workshop. I love the place. I love what you've done with the place. Um, Personally, it's also a sort of an interesting opportunity for me to reconcile with Blaise Pascal because, well, I imagine most of you from Pascal by the unit for pressure, I imagine. But anybody with a French education did not learn Pascal that way at all. Turns out that Pascal had many facets of his life, but one of them was being very religious. And so anybody with a French education read Pascal, philosopher, or how could I put this? The sort of person that uses kind of like scientific logic to argue for the existence of God. And that's how we learned about Pascal in school, which was a pretty traumatizing experience for me. Yeah, anyway. Um, yeah, good. So let's get back to business. So today what I'll talk about is some work in progress with Alex Maloney, that's at McGill, and Florian Siffeld, which is an excellent, well, currently master's student at EPFL, and he's in the process of applying for PhD. And let me start by just reminding something that you all know, but we understand now two-dimensional quantum gravity in ADS very, very well. And so if you want to compute, let's say, the thermal partition function, you sum over metrics, and you put, let's say, the boundary condition that the boundary of the space-time is a circle. And the prescription that now we understand what this is dual to in the boundary theory, and what you would have naively expected from all other instances of ADS CFT is that this would be given just by the thermal partition function of the dual CFT, but this is not what happens in two-dimensional quantum gravity. And instead, what you get is not a definite partition function, but rather a matrix model where you integrate over Hamiltonians with some probability measure P of H, okay? And this is different from all other instances of ADS CFT because this is not quantum mechanics. This is not quantum mechanics is what you do with a fixed Hamiltonian, but this is a probability distribution over Hamiltonian. Okay, and it turns out that two-dimensional, that JT gravity is simple enough that you can actually just compute this path integral and figure out what the matrix model that it's dual to. And the question that I would like to ask today is, okay, that's how two-dimensional quantum gravity in ADS works. So can we go up one dimension and ask, what is 3D quantum gravity? Now, I do realize that we have a discussion session tomorrow with exactly that title. So I'm going to try to not overlap with that too much, but what I'll discuss today is, I think, a slightly alternate approach to what's been going on in the last couple of years. So we've also made some progress here, as I'll mention in a few minutes. But I'll discuss alternate approach, and hopefully it can connect to a lot of the things that we'll also talk about tomorrow. Okay, and I think it's worth pointing out that there's some interesting similarities between 2D and 3D. You know, in both cases, there's no local propagating degrees of freedom.
You mean pure quantum gravity?
Yes, pure.
Oh, you're
pure.
here.
Yes, sorry. Kind of important, actually. I shouldn't write it that small, but yes, pure. It has no local propagating degrees of freedom. The only degrees of freedom are expectations of the boundary wiggles, which, you know, here we refer to as the Shortchin modes, here we refer to as boundary gravitons. The solution to the equations of motion, the classical solution to the equations of motion are locally ADS, but include very interesting topologies, plus boundary wiggles, I should say again. But include very interesting topologies. In 2D, you can do even better. Shell, which is even better. But these are sort of closely connected similarities. And so I think there's, you know, good reasons to believe but I guess we'll discuss this in a lot of detail tomorrow, at least I hope so, to believe that 3D gravity, 3D pure 3D gravity is also an average. Okay. And on top of just the sort of similarities between two dimensions, so I should have said this part is important because it tells you that it's not inconsistent to think that you could UV complete quantum gravity without adding other degrees of freedom. If you have propagating gravitons, then usually there's UV divergences and it gets much more complicated. But here you don't need to worry about that. So there's similarities between these two things, but there's also other things that make you believe that, other arguments that make you believe that 3D gravity could be an average. One of them is that the density of states, if you compute it, and this was done by Maloney and then by Maloney and Keller, so we often refer to this as the MWK density of state is continuous. So this is the density of states that you get by summing over topology or summing over manifolds that are solutions to the equations of motion with a torus boundary. And you get a continuous density of states, which might worry you if you're trying to find one discrete compact CFT whose rule is 3D gravity. But if you think about it as an average, this is not a problem. This is what happens all the time when you average over a Hamiltonian. The resulting density of states. Reinterpreting the result of Maloney, Witten, Keller from this new averaging perspective, it's maybe not so surprising that the density is a continuous function. There are other interpretations. So I'm not saying this implies that it's an average, but it could be a very logical consequence of gravity being an average. Absolutely, yeah. There exist Euclidean wormholes. That extrapolate between more than one asymptotic ADS boundary. And we were very confused about that for, I don't know, I guess almost 2 decades. But that, again, now this has a very natural interpretation if you think that the quantum theory is an average or a probability distribution over theories, because then partition functions on disconnected boundaries you just do not need to factorize. And there could be many other reasons that you may like for you to think that gravity is an average. Okay? Pure 3D quantum gravity is an average. Now, I think it's important to also emphasize the big difference between 2 dimensions and 3 dimensions. And on the boundary in d equals to 1, we have quantum mechanics. And in quantum mechanics, every Hermitian matrix is a consistent Hamiltonian for the theory. Okay, there's no conditions on the matrix that dictates the dynamics of your theory other than the fact that it's Hermitian. Okay, so any H is a consistent theory. Of course, if you pick a particular basis for the Hilbert space, you can put in more constraints like people do on spin chains and talk about locality within the Hilbert space. So you can, if you want to impose more structure on the Hilbert space and constrain the spectrum of Hamiltonians, and this is what people do in SYK, it's a particular type of random matrix theory, but with constraints on what we allow the Hamiltonian to be. That's fine, you can do that. But any Hamiltonian is in principle consistent. Okay, there's no problem. So it's not bad to average over all the Hamiltonians with some probability distribution. This is fundamentally different in higher dimensions. In d equals to 2, the boundary dual should be a conformal field theory. A conformal field theory is highly constrained, infinitely constrained. Yeah.
The H's down and below. Because we could choose some Hamiltonian which has arbitrarily non-equal eigenvalues and the average. If we included that in the average,
You're saying trying to pick a probability distribution that lets the eigenvalues run away arbitrarily far, something like that? Yeah.
So, do we want to exclude those H's?
So what will happen in practice for most reasonable probability distributions, those H's will be excluded by dynamics of the potential. Those are sort of limiting cases in the space of Hamiltonians where you imagine taking the eigenvalues and sending all of them to infinity. Well, I don't want to say that they're measure zero, but they're sort of a very exotic parameter space. And under most natural probability distributions, they just don't happen. The way I would say that is just you have to be a little bit careful what you pick your probability measure to be because you want to get out reasonable things where there's no runaway behavior for the eigenvalues.
What Hilbert space do you expect at least Hamiltonian back?
What Hilbert space? Well, I mean, you pick dimensional Hilbert space and then the matrix acts on the Hilbert space in the usual way.
Then I don't see why the answer to that question is that these are pushed up from exotic regions now because Hamiltonians which are not bounded below are pushed up from far off region in parameters.
Are you thinking about finite dimensional Hamiltonians or?
Inverted harmonic oscillator type Hamiltonian.
Yeah.
You're going to have problem with it.
That's an infinite dimensional Hilbert space, right? So that's.
I mean, I could choose my Hilbert space to be L2 on some space. Why?
No, that's fine. I mean, we do that in quantum mechanics all the time. I was starting in a maybe simpler setup where you think about the Hilbert space dimensional.
Well, you made a stronger statement. You said that is true in quantum mechanics. It is a finite dimensional problem.
Sorry, the fact that any H is allowed in quantum mechanics. Yeah, I would. You want me to add finite dimensional for with that?
I mean, that's why I'm asking you what Hilbert space do you want to?
Yeah, let's start by making the Hilbert space finite dimensional as a first step. Then you can think about how this is supposed to apply for infinite dimensional Hilbert spaces. And there it's clear that, depending on the Hamiltonian, like you say, the inverted, I mean, then things can be tricky, right? But I think if you're on a finite dimensional Hilbert space, then there's not really so much room for that to happen. Would you agree? Well, so no, okay. So there's a little bit more fine print that goes into the statement. Is that you can sort of start with a finite dimensional Hamiltonian, and then you take a particular limit where you make it the double scaling limit. You make it infinite dimensional, and you take some scaling limit of the parameters and the probability distribution in the right way, and that's what arrives at this. But that's sort of different in nature than starting just with even just a harmonic oscillator, which has an infinite dimensional Hilbert space to start with. Yeah. Well, exactly. That's where that. So I think the major difference here is that it's infinitely constrained. We'll talk about that well, actually, I won't talk about that too much today, but maybe I'm hoping that you guys will talk about that tomorrow. But I'll say some words about that in just a second. Okay.
I don't think you want to be saying that any quantum mechanics is equal to
That's not what I'm saying. No.
There's still some, so it's a little bit too loose to say any H is any H is a
No.
theory, but it's not dual to some gravity.
Yeah, that's correct.
That's correct.
But the point is that you can still define the probability. I mean, the outcome of whether or not this will match gravity depends on what you put for P of H. I'm not saying that a random P of H produces 2D JT gravity. What I'm saying is just within the space of all Hamiltonians, you pick some Hermitian D by D matrix, you're allowed to think about quantum mechanics with that matrix as your Hamiltonian. You do not violate any consistency conditions by doing that. So when understanding the space of consistent dynamics, any Hermitian matrix fits in that scheme. This is not true in 2 dimensions because 2D CFTs are constrained by crossing symmetry and modular invariance. And so if you take a random spectrum, for example, you will not satisfy modular invariance. Okay? So this is a fundamental difference where here any Hamiltonian is sort of good enough. Here this is just not true.
I would have said that many H's are consistent quantum mechanics, but not all of them are due to gravity. And then there's a statement that not every spectrum is a CFT. Okay.
This is also true here. Even within the space of modular invariant spectrum, also not all of them are dual to pure gravity. That's also true. But here you have the additional worry that not all spectrum are just consistent to start with. So it goes sort of in step. First, you want to understand what are the space of consistent theories. Then you want to understand within that space which of them are dual to gravity. And that's where I'll go. But you have extra issue to think about, and that's very important. Because if you just try to cook up some random matrix model for a 2D CFT, most instances will violate it. So that's what I'm trying to say. Whether or not a typical one is dual to gravity or not, that sort of will be the point of my talk, trying to address that question. Okay, so good. So the way that this has been approached over the last couple of years, and very interesting progress, and this goes back to Eric's question, trying to understand, okay, what is the data that goes into a CFT? I think we understand this, at least at the local level. A CFT is described by the spectrum of local operators with their scaling dimension and spin and OPE coefficient. Okay, and the approach, which comes in different forms and with different names, but roughly speaking, all of them think about it in the same way. So many people have worked about this in this group, including myself, is to think about a probability distribution over the space of scaling dimensions and spin and OPE coefficient. Okay. And if I erase this part, this is not so different than what we do in quantum mechanics up there, where we think about a probability distribution over the spectrum. It has the extra input that you have to spin to worry about, but you could work spin sector by spin sector. And then in each spin sector, you can think about a probability distribution over the eigenvalues of the Hamiltonian. So this part is not so different, but this part is really new. This part, yes. 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 But you can imagine, yes, you can imagine truncating that space as a regulating step and then moving forward. Yes. Yeah. So maybe it's more like what Mukun was saying, an infinite dimensional quantum mechanics to start. And then you have to worry about runaway behaviors and so on and so forth. So there's really, I would say, sort of two new ingredients. First of all, is that you have to think about these guys, and these are relating to and to how operators fuse. And then both of them together need to satisfy these constraints. Okay, so if you want, you have two new ingredients compared to quantum mechanics, is that you have to deal with these OPE coefficients, and you have to worry about the spectrum and the OPE coefficients together satisfying these constraints. Okay, and so you can sort of cook up some probability distribution for these things. For example, you can specify the moments these things. You can say, for example, that 2 dimensions, the mean of the density of states is the Carty formula, and the OPE coefficient satisfy the generalized Carty formula, the C0 formula for structure constants, or the ZZ formula. And if you think about it that way, you match a lot of nice things. So again, my plan was not really to talk about this. I imagine we'll hear about this tomorrow. But you can do some nice things. You can match gravitational saddles at large C. This is true of the handle body geometries that we already knew how to match, but also of Euclidean wormholes. Maybe I'll write it. You can even do better. As Scott and friends taught us, you can even do this at finite C using a 0-0 topological quantum field theory. So this is finite C. It's a probability distribution for the OPE coefficients and the spectrum. Yeah, so the way it's implemented in practice is by specifying the moments of these things. And by the time you specify the moments of these things, you have continuous function. So it's a little bit like after doing the averaging up there, you produce now a continuous spectrum, and you have a continuous function, Ijk, and you say the second moment of the Cijk is the C0 formula. And then you can refine the ensemble and talk about the higher moments, and so on and so forth. Yeah, so there's various, I guess, various people in this room have thought about it in different ways. The way we like to think about this is as a space of approximate CFT. Okay, so you try to find data points here that come very close to satisfying the crossing equation. And then you literally think about it as a probability over these entries. It's a huge dimensional parameter space, and you think about the probability Herman, and then yeah. No, first of all, I would not claim to solve at all. But certainly the problem has not been solved in a way that takes into account integrality of spin. So the current, or some of us here are working towards that, but the current version with that discretizes spin is not worked out, I would say. No, the continuous J, I would say.
Yeah, it's treating topology by topology, and there you don't see that discrete. See that you need to do some
What roughly, yeah. For there, you can do it. For rho MWK, you can get the integrality of spin because you sum over an infinite number of manifolds. But yeah. Yes. Yeah. A single saddle will not produce, but now you can imagine summing over many of them and building that into the ensemble, and we're doing that. Progress of doing that, I would say. Yes. It's a parameter. It's a parameter of the probability distribution. So the moments of these things, I mean, I imagine we'll hear about that in more detail tomorrow, but here there's some, for example, you can take a Gaussian distribution for the Cijk, and that depends on two things, the weights of these three operators and some external parameter, which is C. So it's cooked into the probability distribution. Oh yeah, I'll talk about that quite a lot today, but at this stage, yes, C is a continuous parameter that you pick to be whatever you want. Yeah. I will not really planning to, but I want to take a different approach to this. I'm just sort of giving an overview of what has been done. No, I don't think, I mean, okay, maybe different people have different views on this. My view is that a draw from this ensemble violates crossing. Even probably a typical draw from this ensemble violates crossing, and then you can try to squeeze the probability distribution in the right way. It depends sort of in what kind of scaling limit you are. But you can try to squeeze the probability distribution to get closer and closer and closer to something that satisfies crossing. And the endpoint of that, I don't know. The endpoint of that is the solution to the bootstrap. So, it depends on what the space of CFTs is, and we don't know. Not exactly, no. So I didn't want to present it this way because this is only my view. I was trying to give an but I think about this as a space of an approximate field. You think about a parameter space that comes very close to satisfying crossing, but you don't impose that it satisfies exactly crossing. Yeah. No, probably not. Well, I mean, basically everything that we know, well, maybe some people disagree in the room, but I would say that basically everything we know about 2D CFTs is we're taking the rational case and we're all collectively praying that we can extend the words to irrational, but I think we don't really know. But if you can do that, for sure, one price that you have to pay is you have an infinite number of equations. So there's an infinite number of data, and they're infinitely constrained in some way that's hard to say too many precise. Yeah. That's what I'm going to try to do. And I don't want to, I'm going to spoil the message before my talk, maybe not quite yet. Before my talk, but maybe not quite yet. And let me just say one final thing is that in a paper that we wrote last year, we wrote something called the tensor and matrix model, because these are matrices, that is more like that thing up there, more like some actual probability distribution over some degrees of freedom, which are now the tensor and this. And they connect a lot of these things together. But they, again, suffer from the same price that finite, before you take some weird scaling limits, at least you probably violate crossing at least a little bit. And so you have to worry about that. Okay. And since everybody asked, let me go to what I do want to talk about today. So I think we'll hear more about this tomorrow. I hope a little bit. But let me say what I want to do today. So it's sort of an alternate approach. And what I want to try to discuss is the idea of averaging over CFTs. This time, actual CFTs. At a given central chart, okay? Or probably I should say in some window of central chart, but I'll talk about that in a little bit. Okay? Now, so this is different. Now we're not thinking about the probability distribution over data. We're thinking about the probability distribution over series. We're going to need to say what that probability distribution is and how we define it and whether it makes sense and so on and so forth. But it's sort of a different concept. And because we're averaging over CFTs, we have the advantage that this part is built in. Now we're just sort of declaring. So this is your question. You can just sort of declare by fiat that you want to only average over theories that satisfy this exactly. What that does here is not so clear, because now probably, these things get discretized in some points, and maybe it's not nice to have some kind of continuous probability distribution over the data. But at least you're guaranteed that you solve this. Okay? So maybe two comments. So this is not like, it's not 100% orthogonal to the other approach. Because, of course, maybe there's some limiting process of this tensor matrix model that still gives you sort of at the continuous function where you kind of impose crossing. So in this tensor model, basically what you do is you square the crossing equation and input that in the probability distribution. Okay, so you're suppressing data that violates crossing exponentially probability distribution with some sort of finite size exponential. Okay. And there might be some limiting process where you can do this and recover actually true CFTs. So it's not 100% orthogonal to that. But the advantage is that constraints are built in exactly from the get-go. Okay. Okay. So but constraints are built in. Okay, and the issue or the challenge is that now you need to think about finding a probability distribution over CFTs. That's a little bit harder than finding probability distribution over data that can, in principle, might be continuous. Certainly, is allowed at the level of data. And so maybe now I can spoil what I'm going to say. So I'm going to try to do this, and I'll spoiler alert, it's not really going to work. So sadly, this does not seem to work. Yeah. So sadly, the average over all, yes. So sadly, it's easy. It's this. And work, what I mean by that is that I'm going to, spend some time defining a measure and so on and so forth. But, once all the dust settles and I give you a measure, and we can ask now within that measure, we average over all CFTs. Is it true that pure gravity comes out? And the answer is no. Okay, so it does not seem like it's true that pure gravity is the average over all CFTs. But why am I still giving this talk? It's because I think there's some interesting things to be said along the way. And so I want to sort of take you along the way of what are the challenges, why it fails, maybe how we could potentially try to go around them, even though I don't see, yeah. The naturalness of them, we can, maybe let's discuss it when I'll write it down. It's hard to decide what the measure should be from first principles, and I'll write something that I think seems natural to me, and I think you would all agree that it's the first thing that you would try to write down. Whether it's the correct one, I don't know, but yeah. Okay, good. Um, very good. So how am I doing with time? I'm probably super behind, but that's half an hour. Okay, not bad, not bad. So what's my plan for today? So this was sort of my introduction and motivation, and now I'm going to spend a little bit of time trying to discuss how we define this measure on the space of CFTs, and I'll make some comments, by the way, along the way on the space of CFTs. Some things that were not too hard to find, but that I did. Maybe some of you knew this, but I didn't, and it's already kind of surprising / interesting, just about the space of CFTs in general. And then I'll try to discuss this question. So basically, if something like this were to work, what it would mean is that within this measure, a typical CFT looks like pure gravity. Okay, that's what it would mean for this program to be successful. And you sort of figure out what the space of CFTs is, you give your probability measure, and for anything like this work for 3D, it would mean that the typical one looks like pure gravity. Large gap in the spectrum of scaling operators, blah, blah, blah. Okay, that which is what will not work, but it begs to ask the question, what is a typical CFT? And I don't know how to solve that in general because, of course, talking about a typical, we don't know all solutions to the bootstrap, even in 2D, even with all the generosity of Jim Simons, we have not solved that problem. But so the best I can do is talk about typicality in some cases of CFTs that we do understand the landscape. And I'll give two examples of that. One is permutation orbifold, and the other is chiral CFTs, or lattices for chiral boson. And there we can make some quantitative statements. Okay, but any question on the motivation? Question? Yeah, possible. Here. No, here the claim is not to say that these are supposed to be dual to pure gravity. Here the idea was to say, within some space of theories, how likely I'll talk about what are the conditions that I impose, but it's like, within the space of theories, how likely is it that a theory has certain holographic properties? Certainly not. I mean, none of these we know are pure gravity. But I thought you were asking about the more general. Was it unreasonable to think that gravity could be the average? I mean, that's a question of belief. I think it's the most natural generalization to the thing that I just erased. The average of all theories, if you go up one dimension, is sort of this, I would say. Yeah.
At least a statement when it's true that every string theory has the one in the factor. It hasn't revealed that the dominant is one factor. Meaning the long distance heavy mass. So right.
String series in ADS3, you mean what?
Things that are holographic, that we call holographic tools. String theory, they have a gravitation.
Yeah.
And that's what gravity really actually universal. That all the systems which we have on
I agree with that. Yeah.
So that's the real statement that we kind of know is true. And then the question is there such a thing as a theory that provides the common denominator of all the factors without adding any other structure?
Right. And that's not so clear, right?
Not so clear that it even exists.
But even putting pure gravity aside, you could even talk about the question for holographic CFTs. You could say within the space of CFTs, how likely is it that this universal sector ever is a good description of the physics? It's always there, but maybe it's polluted by a lot of other mess that happens at the same scale.
It is always, there's always something, but I'm sure that they're going to be redeemed with that dominant. That happens in the black hole. The thermodynamic black hole will become high. But there are certain properties like gravity.
You mean like very high temperatures for the BTZ black hole?
Yeah, anytime where you can.
Right. But so I would argue that's a bit built in by symmetry, because that's just saying all 2D CFTs have a Cardy formula that's true at sufficiently high energy. And the non-trivial aspect would be to say what's the probability that you can trust the Cardy formula all the way down to the Hawking-Page transition? Can you find a probability distribution for that to happen?
You try to approximate your gravity theory as much as you can.
Yeah. Yeah, for pure gravity, you need a lot more than for holographic. You really need to say that there are no light states all the way up to delta order the central charge. That's a lot to ask. And maybe that's why it had to fail. I don't know. I just want to make one comment, maybe, is that the space of things that we know and the space of things that exist are very different. And I do realize that there's, a program. Well, we're recorded. Okay, let me not. I won't continue. But it's very dangerous to take the space of things that we know and try to extrapolate that to the space of things that exist. And I think the best example of that is the Narayan theory. Like we had the task to try to construct some lattice with a very large gap, and we just failed. Okay. And then what we did is we averaged over all the lattices, and we found that the typical one has a gap of order the central chart. Okay. So that's showing us that, within the space that we know how to do, we were just completely off, right? Like it's like huge lampposts. Like so it's kind of dangerous, and that's the worry in this business, is that we don't understand the space of CFTs, and so it's tricky to try to make any claim like this. But what I'll show you is that even with things that we do understand, there's something seems to go wrong. Okay, good. So let's talk about measure the space of CFTs. So, the thing that we'd like to understand is you integrate over conformal theory space. Presumably, you take the central charge to be in some small window. I believe that ultimately the central charge should be discretized in 2D CFTs, at least those with, a normalizable ground state and a stress tensor and so on and so forth. So if you don't average over some bin of central charge window, this is going to be a very badly behaved function of C, because, you move a little bit, you have nothing, then you arrive at some, so it's the safer thing to do is take some, you can make this very small, and actually I'll show you some result of how small you may need to take this. But this is the safer thing to do, and this might be sort of kind of smooth as a function of C0. Okay, and then we want to have some probability measure over the space of CFTs. Okay. And what do we want to demand? Demand two things. One, that the measure is positive. And two, that the measure makes sense, that it's normalizable, that you get a finite number when you integrate over it. Otherwise, it's not clear what you're doing if you just get infinity. Everything. So compact, unitary, modular invariant, crossing symmetric. Am I missing something? Yeah, I don't know. Nothing. No sort of more fine. I mean, I'll talk about this infinity. So I'll talk about constraining that in a little bit, but no twist gap or nothing like that. We really want to average over everything with no a priori constraint. Yeah. Oh yeah, I'll talk about it in a second. So CFTs come with families, and we'll have to yes. Okay. So very good. Actually, let me talk about this now. So what I think is the most natural guess is the following. So in some charge window, you're going to have, in principle, both things. You're going to have discrete isolated CFTs that are points, and you're going to have manifolds. Okay. So what you do is the following. So what does it mean? The definition of this measure is to sum over the discrete part of the CFTs. Okay. And I'll talk about two measures. But for now, let me do the one where you just count them as one. Okay. And then you also sum over the continuous, the family of conformal manifolds that appear in this bin. Okay. And then you weigh them by 1 over the volume of the conformal manifold, where the volume is measured with respect to what I would say is the natural measure on the space of CFTs, but this, maybe you want to argue against, Scott, I don't know, which is the volume measured in units of the with the Zamolodchikov measure on the space of CFTs. Okay, so integral of square root of g, where g is the Zamolodchikov metric. And then you just weigh them exactly in the way that I said. Okay. Okay, so as all discrete CFTs, you have one, and all continuous families of CFTs, you weight them with the volume. Okay.
You have to model by dualities.
Here, yes. Like you mean like I mean dual. Yes. You take a fundamental domain of the conformal.
Even the discrete part, they'll get a trouble for literal model.
I'll talk about that. Yes. I mean both cases.
Yeah.
Oh yeah, I'm putting nothing by hand. You could impose additionally some amount of supersymmetry, but this will treat supersymmetric one, non-supersymmetric ones in the same way. You might have a hard time. Well, I guess in 2 dimensions you can have conformal manifold without supersymmetry, but if like if you enforce some amount of supersymmetry, it could change what happens here. I'm just averaging over everything. Okay, and so this is the most natural measure for me. Not everybody in our collaboration agrees, I guess. The most natural measure for Alex, and I'll explain why, is the one where, so this associates to every CFT the number 1, okay, which I think is pretty natural. There's another measure that you could put, and actually this is sort of more consistent with what comes out of the continuous parts, where you label them. So a CFT can in principle have a non-trivial automorphism group, okay, and you can weigh them by the size of the automorphism. Okay. Yes. Here, you mean because of singularities on the conformal manifold? Yeah, well, I think we sort of still understand kind of poorly the allowed types of singularities that occur on conformal manifolds, and so I think the best I can do is sort of wave my hands. There's some conformal manifolds that we understand, for example, the Narayan ones, and we can integrate over them, and we understand the singular points the types of singular points that could appear, and so on and so forth. But yes, it's true that in full generality, what are the type of singularity structures that exist on conformal manifolds? I think it's an unanswered question. Okay, so you can either put this factor, not put this factor. It won't change so much the outcome of what I'll say, but I mean, I think I would be happy with it as a first step. Good. Yeah, so this is what I'll talk about at the very end here. Chiral CFDs, the sort of natural things that, the Siegel-Vive formula spits out is this. And so I think that's why Alex likes it. And if you sort of look at the local density of, so, you can have fixed points of this symmetry group that Connor was asking about on the conformal manifold. And if you look at the fixed points and the sort of value of the local measure near the fixed point, it's sort of always weighted by this thing. So that's why it's unnatural to think that this is the right measure. But I think I would be happy with either one at this stage. It's true that this one is nice, this nice does not necessarily mean fundamental, so I would be happy with either one. They won't change too much the conclusion. Well, they won't change the conclusion. Okay. What's the problem? That this is infinity. Okay. This does not. It's related to an ask, and even if you look at the simplest example where CFTs are classified, which is C between 1/2 and 1. There's two problems. There's an infinite number of minimal models. So there's an accumulation point of, as you know, the minimal models have central charge, which is 1 minus, 6 divided by m times m plus 1, and they approach c equals to 1 in the large k limit of or the large m limit of the minimal models. So there's an accumulation point of CFTs here. So this gives you infinity. And on top of that, the free boson, which is also there at c equals to 1, has a conformal manifold with infinite volume. Okay, so you get infinity plus infinity. Okay, so this plus, the integral from the self-dual radius to infinity, where the Samologikov metric is 1/3, so the volume is computed by the following thing, and this is infinity. Yeah, that's how I'm going to, a twist gap. Yes, I guess. I'm just going to impose gap, actually. On delta, but yes. Yeah, that would be pretty natural to, yeah. Yeah, the Swiss gap would take care of all of that once, I guess. That's right. I mean, this goes back to the question about supersymmetry with, fix the symmetry algebra or not. I would ideally think you don't maybe need to, because maybe the ones with extended algebra are rare within the space of theory. Who knows? Yeah. But you can't make this finite. I will make it finite in a second. Yeah, so no, I don't think the central charge is the problem. That is a measure. Yeah, with a measure, right? Which I'm telling you how I'm weighing each matrix. You mean, well, the Gaussian part is the measure, right? It says that if you take the matrix element Mij and try to make it infinite, or 10 billion, right? You're going to be, it damps it. That's a continuous case, so maybe that's why you're not really seeing this as a measure. But this is sort of telling you each of the CFTs how you count them. It's discrete, so I think the thing that's more like the measure that you're talking about with Gaussian is in that square root of g part. That's more like a continuous function, which was not square root of g, but some other thing that you use on the manifold. You could have a similar problem as a flat potential. Well, then I don't know what it means to, if you don't have like in any probability distribution, it doesn't integrate to 1 or some finite number that you can normalize. I'm not sure exactly, what to do. The first thing that it would require is that it gives you a finite number, like the probability sums up to 1. to something that you can normalize. If it's infinite, I'm not sure what to do. What I'll do is I'll introduce a regulator. And so then you get a finite measure. And what you can do is compute some observables and then try to take the regulator to zero at the end of the day. Compute integral d mu something divided by integral d mu. Both top and bottom are finite. And then you can try to take the regulator to zero and see if you get something convergent or not, which I don't know how to do. I'm not going to do that, but try to do that. Okay. And so this problem here, of course, this was just a problem between 1/2 and 1, but this problem extends to much higher central charge because now what you can do is take any CFT that you like, tensor it with any of the minimal models, and get another accumulation point. For example, there's an accumulation point there at 1. There's another accumulation point at 3/2. So you take the Ising model and you tensor it with any of the other minimal models or with the free boson and you get another accumulation point. For the free boson divergence, you have to be a little bit careful what you tensor it with, because if you tensor two free bosons together, there's an enlarged conformal manifold, and that one is actually finite volume. But still, just by tensoring in minimal models, you can get divergences. So the problem persists to higher C. And in fact, you can calculate or you can bound the density of these accumulation points as the central charge becomes large. Okay, and you can do that just by figuring out what's the optimal way to tensor minimal models together to sort of close in the windows of accumulation points at large central charge. And then there's this result that I find quite nice, is that, so this is the difference in central charge between two accumulation points where there's an infinite number of CFTs, and it decreases doubly exponentially in the central charge.
That's just the middle.
That's just for minimal models. Okay, so there's well, Florian, I mean, he worked kind of hard to derive this, but it was a very simple fact. And this is a bound on the number of accumulation points, but it immediately implies a bound on the distance between CFTs. So CFTs are at least doubly exponentially dense. Okay, and this you get by tensoring and minimal models together. So it's almost free lunch. And I don't know if anybody knew of a bound. And it's very interesting that it's doubly exponential in C. I don't know if there's any interpretation of that with respect to gravity or not, or what we make of this, but I find it pretty cool. That's the largest limit. Yeah, this is as well. You can derive if you put in the right numerical factors in the right place, you can derive some bound that's valid at any. It's just a recursive formula where you start from 1/2, which is the gap between 1 and 3/2, and then as you go in central charge 1 by 1, you make it smaller and smaller. You just solve some recursive formula and you derive. Yeah, it's also the distance between CFTs, but it's both of them scale in the same. Sorry, can you ask that again? Yeah. I don't know. I've argued both sides of this debate, depending who I argue with. If I'm talking with Eric, I try to play devil's advocate and say, how do you know that it's not continuous? But I believe that it's discrete at the end of the day. But I don't think we have any proof that it is. Maybe you would disagree with that. I don't know if you want to weigh in, but
it isn't just a bound, right? Like maybe when you say that almost right, but and it works.
Yeah. Yeah, it tells you nothing about whether it's actually continuous at the end of the day or not. Yeah. Yes, there should be, right? Well, otherwise it grows, right? 3/2, 1/3/2 to 3/2. Yeah, I'll talk about that actually here. Yeah. Yeah. My guess is that the more you sharpen it, the less you'll be able to say, because then you'll be back at saying, well, okay, now I've put a lot of constraints in, and now I don't know anything. So yeah, I think what you might be trying to say is that, here we're polluting. So maybe we failed at deriving pure 3D gravity, but it's because we polluted it with a lot of really bad theories, and that are maybe stupid, both bad and stupid, and that really we should do. Okay. Um, and one other thing that I'll say is that this is true for this. These are all rational because they're just tensoring minimal models together. But there also exists accumulation point of irrational theory, and that surprised me even I think a bit more than this. So here's an example. Nathan's gonna. Uh, no, more true irrational. No, super zero zero. Okay, so here's the example. So you take the supersymmetric minimal models, the kth one or the mth one, whatever you want to call it. You tensor three of them together. Okay. The orbifold by S3. Okay. And in each of so the limiting sequence will now be to take k goes to infinity. So as k goes to infinity, the minimal models go to central charge 3. So this total thing goes to central charge 9. And it becomes dense. I mean, it becomes very, very dense as you send k to infinity, approaches 9. And in each of these theories, so these theories are very complicated. I cannot tell you anything about the global structure of the conformal manifold, but what I can tell you is that at the orbifold point, every single one of these theories has a twist-3 marginal operator that you can turn on and move away and produce what I think, at least in perturbation theory, is an irrational CFT. So the statement is that there exists an infinite, so there conformal manifold, there's a dense accumulation of conformal manifolds. And on each of these conformal manifolds exists, I think, an irrational point where the only symmetry that prevails is super zero. And it becomes dense. Okay. Okay. So what is the dimension? Yeah, I'm super glad you asked that question. It's another really interesting point, I think. So, all of these stuff are kind of like curiosities that I don't know, tensoring stuff together. It's not too hard, but what comes out is really, so exist irrational points for any k. Okay. So you have a dense accumulation. And yeah, you can ask what is the dimensionality of the conformal manifold of these things, and it grows. It grows like k to the k squared, I think, as k becomes larger. And that's another really interesting thing is that we have CFTs of fixed central charge with unbounded dimension of the conformal manifold. I guess it's in our paper, Nathan, but I never realized that it was there until recently. And I think this is also a bit surprising. Like Simeon has a paper about the modular bootstrap and trying to derive some bound on the number of marginal operators that you can have at fixed central charge. It's some function of the central charge. He makes some assumptions that don't apply here. He makes the assumptions that there's no relevant operators. These are full of a ton of very finely spaced relevant operators. But he's sort of saying, it would be very unreasonable if there existed a CFT of central charge 2 and 10 to the 200 marginal operators. And here I'm telling you that there exists a CFT with central charge less than 9 and an unbounded number of marginal operators.
I think we even found a good explorer.
Oh, really?
I think there are also some examples of 40 and equal to.
Oh yeah, no, but the e to the k one I think is sort of different because it's like in the.
No, I think I think it also found it had a 6.
Oh, it also had a 6. Okay, well then it's even worse. It grows exponentially. Yeah, okay. That's why I was sure you would remind me. But so I think this is also very interesting and very surprising. These I think don't give you any problem. So you might be worried about this, but this is a very high dimension conformal manifold. I think it doesn't give you any problem because actually the volume of very high dimensional conformal manifolds decreases with the dimensionality. For supersymmetric theory, it's quantized, and so I think this will go like C to the minus dimension, something like that. So these will occupy a very small portion of the measure space. Oh yeah, yeah. So in each of these theories, there's a twist-free marginal operator, and these do not come from this. Where these come from are untwisted sector marginal operators. So each of these theories has a bunch of BPS operators, and you can tensor them together in a way to get some operator that's exactly protected that you can use to do conformal perturbation theory. And the number of the operators grows because you can combine them in different ways to get an operator of dimension 2, a protected operator of dimension 2. And so this is where the sort of, and this is what you're saying with the number of partitions. This is some combinatorics of how to pick VPS operators in each of the copies in such a way that the dimension equals n equals 2. Yeah. Sorry. Yeah. I said it. Yeah. Yeah. Yes. Yeah. So the conformal manifold is basically all of these guys plus this, and maybe plus others that for particular values of K. But I, yeah, I guess so. Yeah. Right. Okay. Sorry, I lost a little bit. Where was I going with this? Good. Oh, yeah, good. So anyway, this was to show you that, first of all, well, there's these interesting things about conformal manifolds, but the space of CFT is very dense in central charge and has a ton of accumulation points, including irrational. Okay. So we need to do something to fix this. And so we need to regulate the space. And I guess a twist gap would have been nice. We didn't really think of that. The way we did it is just to demand that there's some delta min, and that we're only going to look at, so we put a gap, if you want, on the scaling dimension of operators, and only going to allow CFTs that have all scaling dimensions apart from the identity bigger than the gap. Okay? So this fixes the problem because, you know, the minimal models, their spectrum becomes very dense, and there's very light operators that appear as you increase the minimal model. So you can figure out, for example, the number of minimal models that satisfy this goes like delta min to the minus 1/2 at delta min. So you see that indeed when you send it to 0, it becomes infinite, but this regulates this infinity. And similarly for the free boson, you get a log. So the regularized volume of the free boson at some fixed delta min goes like log of delta min. So an interesting observation is actually the minimal models seem to dominate over the free boson in this particular one. Okay. Yeah. Oh, you can do other variants of this with more operators. Like this is the simplest accumulation point. Yeah, I think probably you can take 2 copies. You can already have a growing number. I mean, no, sorry. 3 copies is the minimal place because for you to get irrational points, you need there's only a twist 3 operator. There's no twist 2 operator. That's why. So for you to get some operator that makes the theory become irrational, you need that.
Does it have anything to do with the statement in Hiro-Saro minimum models? When you couple 4 of them together by the spin field, you get some integral flow, but then 5 or more, it's apart.
I don't know.
Like 4 Isings plus 4 sigmas, that's something.
Yeah, here there's the thing is the S. Really, it's important that you take the S3 orbifold for you to have this marginal operator that lifts them. So I guess you're thinking about a different. You want to do like a relevant deformation, which is turning on the product of the sigmas in each copy or something like that. Yeah, that's a little bit different. I don't know if it's related to the fact you're asking whether there's some relation between the fact that we have to take 3 here and you need to take like 5 for you to.
Yeah, it seems like when you take the minimal number, are special. All the other ones.
Yeah. Here it seems to work the other way around because I think here. Oh, you mean for the n equals to two,
Yeah,
two
like,
copy
you
paste?
had to do at least two.
Yeah, yeah,
And we had to do at least four.
yeah, yeah.
Five.
It could be that there's some connection there. Yeah, I'm not sure. Interesting question. Okay. Well, epsilon at this stage was generic. I think with what we derived here, it sort of tells you what epsilon is. So even if you make the epsilon, exponentially small in the central charge, that's still summing over a crazy number of CFTs because the gap is doubly exponential. So I didn't know from first at the level of writing this formula, which we wrote down before that one, I didn't know what epsilon should be. I think this tells you what a reasonable epsilon is. But this is it's part of kind of the definition of the ensemble somehow. I don't think there's a real first principle. I also don't know how to think about what that epsilon means in gravity. I was at first not super sympathetic with the idea of averaging over central charge, which this thing is kind of doing, but I think it's the only way to get a smooth function. At first hand, I would say it's different because here it's just a parameter that we're allowing to vary, but every single member of this satisfies modular invariance. Whether you connect the two in the, yeah, it's an interesting thought. I don't think I have anything quantitative to say. Yeah. So now I'm going to cite one conjecture. If you believe it, will instantaneously kill our hope of. So here's the conjecture. It goes by to Kontsevich, Stoibelman, but also Ashrian Douglas. Sorry, yeah. And the conjecture is the following. So the space in this sense with C smaller than some C naught and with fixed delta min. Is finite. Okay. So the conjecture is basically that now once you've regulated this in this way, there's a finite number. Good question. What exactly they assumed in the original conjecture? Let me make a variant here. Yeah. Yeah. Yes. Sorry, I could have said. The lowest. Why? Well, if we set it to be, yeah, if we set it to be 1.5, then it's true if we set it to be like 2. Yeah, yeah. The idea is to make this very small, right? It's more going to be like 10 to the minus 2 or whatever, like so small. Yeah.
It's finite dimensional.
Finite in the sense that there's a finite number of discrete ones and finite volume moduli spaces for the continuous family.
Then what about your example? Equals 9.
Oh, those get killed because I didn't tell you, but the supersymmetric minimal models work very similarly to the usual to the 0, minimal models. And as you make K large, the spectrum becomes very finely spaced, and it gets capped off in a way that I don't remember from my head. Also, probably some kind of square root of delta min. So you also constrain the space here. Yeah. That you would have to ask them. I think it seems reasonable because what can I say? No, the way things are going wrong in all the examples that we know is really because we're allowing operators to approach the unitarity bound, like delta equals 0. And it always seems to be the same sort of problem. And now that does not mean, I mean, again, I'm not saying that I believe that this is proven or this proof, but I think it's kind of a reasonable assumption to think that this is the way that you run into trouble in quantizing the space of CFTs or you know getting a finite number of CFTs is with very, very light operators. But can't say more than believe, I think. But what I'll show you is that if you believe or don't believe this, in both cases, you're in trouble. So for different reasons, okay? But I think I'm happy. I'm happy to trust it. It seems reasonable, I think. But you know, answering these questions, I mean, we know so little about this completely wrong. Maybe we just there's an infinite number of CFTs. I'll have a lot. Like this could be completely wrong in principle. I think. I don't see any without you know solving the bootstrap. I think we cannot answer this. Yeah.
Where can we read this?
This paper, the sort of toned down version that's very easy to understand in this paper, in like '06, I think maybe in Eric's, even like also like Eric's paper on the distance conjecture, maybe like summarizes it. And then here, and then this is a bit more hardcore, but it's also in
You know
here.
what it's called?
The title,
There are many papers together.
past? No, I forget. I forget. This one is called like finite dimensional, a finite space of quantum field theory. This one has a name that does not look like that's what the paper is about.
Yeah, that's why I'm asking.
And maybe it's not what their paper, I mean, it's only part of, there's a lot of stuff that paper is part of, yeah. Actually, there might even be two papers, I forget, but yeah. Okay. Good. So, okay, so if this is true, conclusion. So if true, well, it's game over. Game over, it's because now let's go to some high central charge, I don't know, 10 to the 300 or whatever, very large value of the central charge. This tells us there's a finite number of CFTs at a given delta gap, which means in particular that there's a finite number of pure gravity-like CFTs with a gap of order the central charge. That number is finite, okay? And now, no matter what that number is, I can then further dial down delta min to some much smaller value to completely overcome the number of true pure gravity fields. Okay? So the idea is that if this is true, it says that there's a sort of finite number of pure gravity-like CFTs at any central charge. And then by suitably dialing this delta min, I can overcompensate that always. Okay? So in any kind of reasonable limit where you take this regulator away, it'll be ultra atypical for a theory to be pure gravity. Okay? If not true, then we fail to have any kind of finite measure. And this is not necessarily game over, just I don't know what to do with this. This is not true, then we haven't regulated the space of CFTs, and I don't know how to regulate the space of CFTs, so I don't think I can say anything. Okay. So okay, so if true, it means so good. So let's fix delta min to be 1. Okay. Now we look at the number of CFTs at p equals 10 to the 300 or p close to 10 to the 300, and we say, okay, cool, there's 10 to the 300 minus 6 pure gravity like ones with a huge gap. Okay, almost all of them are like this, and all of the other ones are just very few. Okay, so now we conclude that there's like 10 to the 300 pure gravity like CFTs at that value of the central charge, the finite number. Now I'm going to take delta min and I'm going to decrease it enough that I'm going to get much more theories like this. So the point is that every time that you try to remove this regulator in any way, you're going to be polluted by all theories that are not at all pure gravity. And in any kind of reasonable limit, there's no chance that you'll see 10 to the 300 theories that stand out. Yeah, so then maybe you can say, so maybe it's not, you don't want to say it's a complete game over. Then you can say, we're not going to try to ever remove this. We're going to fix it to be e to the minus c or whatever, some scaling with c. And then that's part of our measure, and we're going to keep it that way. And we declare that that's part of the space of theories. And then within that space, pure gravity is the dominant answer. That's a stance that you could take. But it's a bit hard to justify because why would you impose this from the gravity perspective? I agree. Yes. I agree, but I agree. With the caveat that you would want a condition like this to be justifiable from the bulk perspective. This is not a UV. This says that you do not allow massless fields in ADS to have masses that are, well, it's not the BF bound, but like higher than BF bound. Things being very close to massless with ultimate bounded conditions or whatever the right thing is. I mean, you can do that, but that's a very IR constraint that I don't see any good reason for. Yeah, but you also don't want to put the answer in by hand. You could say, let me put delta min to be central charge, and then, yeah, maybe a twist. Yeah, you could try to do it with then if you put a twist gap, then you could say, okay, well, that still doesn't tell you that it's gravity-like. Maybe it's more graphic-like or rational-like or whatever, and then say maybe within the space of those, pure gravity dominates. It's possible, yeah, and that's you might argue that maybe a better ensemble, but it's a pretty restrictive. I guess what I'm trying to say is that that's a very restrictive thing to do within the space of all CFTs. Yeah. But the question is, do you want to? Yeah, but the question is, do you want to get rid of that by inputting it or by receiving it as an output? That's the question. I would have hoped. The hope is to receive this as an output. Yeah. Yes. That's what I mean before. I should have said that's what was set up. Like, absolute opposite in the case, but I was hoping that, all these very rational theories are like so special and so fine-tuned, and a little bit the opposite. So you could do what you're saying, but you're inputting it, not getting it as an output. Just fine. Yeah, you can fix your ensemble to be within a given class of chiral algebra, and you can declare that to be just for a graph.
Maybe one good warm-up call. So I definitely agree with your kind of thing that finite surf happens much more muscle, but it helps much more people. We have no idea how. But I think here's a very good warm-up problem. But I think also so interesting that at least we know these theories, which is what's the average of a K3 range? This is now some finite dimensional level. It says we have finite quality. And it's believed that a generic point there has only any proportion. Or you should take a caveat that let's caveat fix. We said a generic function has finite subgraph, which is that the volume can have that finite. So there you can have, if you could somehow, I don't know, but if you could somehow ask what the average number of the number of places, I think that's a good one between the general cases, maybe two for real, so before the text of it, and it's generic.
And you think the fact that in T4 it's dense but measures, the fact that it's dense but measures 0.
Yeah, I don't think because T4 is still T4 the market is still basic.
Yeah.
So I don't think T4. I think T3 will be like the most. Well, the first
want to conjecture anything about what happens when you do that?
No, I haven't.
Okay.
I guess I'm so confused as to what you're calling pure gravity. What do you want for the spectrum of light operating?
That there's a gap of order of the central charge.
That you can have anything, there's a gap.
Yeah. Nothing up until delta of order C. That would be like, that's another condition that you could ask for holographic. That's more along the lines of what I'll talk about. I don't know, I'm probably out of time, but what I'll try to talk about here. But at this stage, yeah, for pure gravity, we would have hoped somehow that the point is that this is like the Narayan cases, right? Like you try to build trees, they all have a small gap, but actually take the average over all of them, and it turns out that the typical one has a very large gap. And it would have been very nice if we got this as an output here, which doesn't seem to happen. That's a fact. That's a fact. I mean, people were not. Somebody maybe some people probably know this better than I do, but I think the best construction that you can do of an explicit lattice with a large gap is what, like square root of C, something like that. And then you take the average over the Narayan moduli space for the Zamorodnikov metric, and you look at what the average gap is, and it's of order C, meaning that most lattices have a gap, but you cannot produce a single one that has that scale. Yeah. So, I think we were driven a little bit by this, is that somehow, space of what you know and the space of what you can construct are very different. The space of what you can construct and the space of what exists are very different. And so maybe, you think about the problem the right way. And actually, vast majority of CFTs have this gigantic gap, but we cannot produce a single one. That was, I think, sort of the logic going in. And maybe it's true in the constrained space. I have no idea to say yes or no or anything. That's the problem. But how am I doing with time?
Sort of statement that the generic vector you would put in the
yeah, it's basic. I mean, there's a way to phrase it like that.
But that belies the fact that if I go in some lattice vector direction where essentially all of the components of the vector turned off except one, then it looks like a circle in that direction. And vectoring has
very small gap, right?
Very small gap.
Yeah.
So
yeah.
That's like a not generic vector. Okay, but it has. But if you're making some statement about like all of the component dimensions are of order C, I'll just gave you one put the letter beside the inverse side of the line. So, statements about what the generic operator dimension is not the same statement with the minimum.
Yeah, but his statement is still stronger. His statement is that a generic lattice has a generic minimum dimension.
Yeah.
That's scalable.
Yeah. Sorry, maybe I didn't say it right.
Maybe counterintuitive, but this was proved by Vigo and Bay.
Yeah, that was my face too. But yeah, very weird. And I'm not sure this is still explained. Oh no, nothing's wrong with your lattice. It's just atypical within the measured space. I think that's the point. The local probability distribution over lattices of the type that you just said, measured in units of the Zamorodnikov, measured by the Zamorodnikov metric, is small in probability. So it's nothing is wrong with your lattice. It's just atypical. And I'm not sure I can say anything. Well, yeah. I'm also confused by it, but it just seems to be true. So you could have hoped that something similar happened here. Yeah, how am I doing with time? I'm out, right? Sure. Well, from 0 to anything. So you do okay, I can make this next part short. Yeah. Yeah. Yeah, but the number, well, yeah, it means the number of isolated finite, but then what do you say about the ones with the conformal manifold? Yeah, there's some, well, depends here or here. The mathiness is, finite stack or yeah. Yeah, no, okay. My interpretation of what they did, and if they did not say that, I don't want to put it in their mouth, I will say that modified conjecture is that the number, as explained in some previous blackboard, that number is finite. So the number of them plus the volume of the continuous one is finite. And you know, I'd be happy if any one of you proves me wrong, if it's done wrong. But well, if it's wrong, it's done, right? Okay, so let me say, since I'm out of time, I'm going to make this just quick, but I want to try to say something a bit quantitative about the space CFTs that we actually do understand. So here's a space of CFTs. They're called permutation orbifolds. You take your favorite CFT, call it the seed CFT, take n copies of it. This has a gigantic automorphism group, which is the permutation of the n copies. You can take quotient by any subgroup of the symmetric group and produce a new theory. And this is what's known as a permutation orbifold. Okay. And the idea is that the product theory has a ton of low-dimensional operators. The seed theory had an operator at dimension 1. The product theory had n operators at dimension 1. And the idea is that if you quotient by a group that's big enough, you can get rid of a lot of these low-lying operators. Okay? But for this, the group needs to be big. So these are called permutation orbifolds, and there's a special class of them. So you can ask the following question. So this is a necessary, what I would call a necessary for a theory to be holographic, but very far from a theory. Necessary condition is that if you fix a scaling dimension and you count the number of operators at that scaling dimension, and then you take the limit as n goes to infinity of this thing, which we often call for infinity, that this converges and is finite. Okay. So what this says is that the number of operators of any fixed dimension in the sequence of theories, you specify the group, converges and is finite. And this is non-trivial. If you take the group to be the identity, it's obviously wrong for what I told you before. If you take the group to be the symmetric group, it is true. If you take the group to be the cyclic group, then it is not true. Okay, so it depends on purely group theoretic properties. It has a name. You can read about it in the paper of Mukund and Felix or in the paper of Alex Christoph and me. It's called oligomorphic permutation group. So they're studied by mathematicians, in particular by a mathematician called Cameron. Okay, and the condition is basically that there's a finite number of orbits, that's the group theory criteria, on K2 folds. Okay. Again, this very crude notion of holographic, because once the spectrum converge, it could converge to anything you want, including something that has a finite but huge amount of light states, which we would not really call holographic. Like the string theory of the ADS scale, or even worse. Yeah, I'm allowing any kind of growth, and I think Beatrix can even have cases where this grows faster than Hagedorn. I forget e to the delta squared or e to the delta log delta. So you can come up with wild kinds of growths that you want here. Okay, good. So now you can ask within the space. You can ask the question within the space of all possible subgroups Gn. What is the probability, or how many subgroups Gn have this property? Now, what is the probability of a subgroup of Sn being oligomorphic? Okay. And you can ask that question. That question is a little bit hard because you have to phrase it so this is not really the oligomorphic condition is kind of a condition as you approach n equals to infinity. So you have to think about it in a sequence sense. And not really sort of at any finite n, which makes it a little bit tricky. But you can do one more thing, which I think is pretty natural. So you can demand oligomorphic plus transitive. Transitive means that there's a single orbit on one two-fold. And what that implies is that there's a single stress test. Okay, and this is, I think, a very natural demand because it means that there's a single graviton in the bulk. Okay, so you can ask about, what's the probability measure of the group being oligomorphic and transitive? Single stress tensor and finite number of states will then go through. Okay, and it turns out that there's theorems of mathematicians that tell you how to bound. Okay, and the first thing that you need to know is that the number of subgroups, so let me call S of Sn, the number of subgroups of Sn is actually bounded. This is a field of mathematics that is actually not very developed, but they still managed to prove this. Sorry. So the number of subgroups of Sn is bounded to be between here and here. And the interesting thing is it goes like e to the n squared. And this is immediately a lower bound on the number of CFTs. A given dimension. So each of these are CFTs. And so the number of CFTs goes up like n squared. And in fact, you even have a lower and an upper bound on the number of subgroups. And this part is hard to bound, the oligomorphic one, like I said, because you have to think about it in a limiting sense. But there's actually a theorem about the growth of transitive ones. And it grows much slower. So the probability is the number of groups like this divided by the total number of subgroups. And the point is that the number of transitive groups grows slower than this, parametrically in n. It goes like n squared over log n, bounded by n squared over log n. Okay? So the point is that P of this oligomorphic and transitive, okay, is smaller or equal than e to the minus n squared. Times a pretty big factor, which is e to the n squared over log n. Sure, it's a big factor, but it's parametrically small in large n numbers. That's the leading order. Okay, so what this shows again, and this fits into the spirit of everything we've been saying, is that it's very hard, it's very unlikely for CFT to have holographic-like properties. We could also lower bound this just by sort of construction. So again, just because the total number of group goes like n squared, you get the e to the minus n squared. And here we found log n to the L for any L that doesn't scale with n, just by explicit construction. You can see that there's a ton of wiggle room between basically log n to n power. Let's even call this e to the log n, which is n, maybe some polynomial in n. There's a huge amount of wiggle room between n and e to the n squared log n. So I'm sure the bound can be vastly improved. We just couldn't do any better than this. But the important fact is really this e to the minus n squared. Okay, so the probability of a theory having a finite number, sorry, this really comes from transitive, of having a single stress tensor within the space of theory is exponentially small compared. Yeah. Sorry, first just talk about transitive groups and then. Yeah, you could do that. We don't know how to do that. It's very hard to sort of bound the number of oligomorphic groups because of this sequencing problem. Is that number of subgroups is not like some continuous function, right? It jumps around. I'm sure there's interesting happens when n is prime. Like it's some complicated thing. And even though you can bound it, you can't. It's hard to make sort of conversation.
That statement only for transitive subgroups. There's no condition of oligomorphism.
That's the lower bound. You can ask how many ones can you actually construct? How many different ones?
Since you couldn't say anything about the oligomorphic, I'm not sure what that bound.
This bound is coming just from this. You're correct. Yeah. I'm sure that if you were able to implement this, it drastically reduces it this way, and I'm sure that you can do better than what we construct. But using oligomorphic for this side of the equation seems too hard for us. And it's important, maybe I didn't say this, is that none of these things are bigger or smaller than one another. So Zn is transitive. You can map any element to any other element with Zn, but it's not oligomorphic. S of n over 2 cross S of n over 2 is oligomorphic, but it's not transitive. So either there are really two things that you need to put on top of one. And think about the space of different sequences that you can talk about that exist at every n. Yeah. Yeah, but it's jumpy not just because of the prime thing. I mean, it's really the structure of the subgroup. Yeah, maybe you can do that. We didn't understand any nice way to do that. And then there's a lot of the mathematicians, what they work on is actual oligomorphic groups, which are defined at n equals to infinity. There's like the isometries of the random graph or whatever is proven to be oligomorphic, but it doesn't mean that there exists a sequence of theories that are right there. And there's very little results that I know of about sequences. The results, they sort of prove at the level of n equals to infinity, countable infinite sets. And so, okay. Yeah, yeah. And these have all gigantic, but at least a single stress tensor seems like a natural thing. Okay, and I'll take 30 more seconds for the chiral CFT case. So there you can use the Siegel-Weil formula. So there are two results. Mathematicians that you can use. The first one is that if you look at the number of CFTs, so if you look at the sum over all chiral bosons on some, even self-dual lattices, sum over all these lattices and weight them by one of the automorphisms. We know the number of this. This grows even faster. So it's like e to the c squared log. And that I know of, this is the strongest lower bound on the number of CFTs. It says that at sensitivity, you have at least these amount of CFTs, at least one different chiral theory. The problem is that these theories, most of them, again, have a gigantic number of states. If you look at the number of states at dimension 1, as you take C to infinity, the typical one diverges. Okay? So then you can ask, okay, what if these theories had non-trivial automorphism group such that you can orbifold by them and reduce the number of states? One example of that would be if you take the monster CFT to the nth power, then that has an SM symmetry that you can orbifold by to get a finite number of states. That's one very small example. And then you can bound this. So this is a result of King. So you sum over the one such that the size of that automorphism of C is bigger than 2, which they all have. The non-trivial automorphism group. That does not guarantee that you can quotient by them to make the theory have a finite spectrum, but it's at least a necessary condition divided by the total number of lattices, and this goes like e to the yeah, these have delta equals 1, so they're zero requirements. It's a chiral theory, right? So they're all currents, but this is the number of U1, the number of conserved current. Yeah. Everything is, yeah. So it's a pure current. It's a chiral theory, so it's a pure current theory. Everything is a conserved current. So in some sense, there are no primaries with respect to the maximal chiral algebra. So again, in this case, we arrive at the conclusion that it's exponentially difficult in central charge to produce something that is holographic-like. Again, holographic-like here is a very, very, very crude notion of holographic, the finite spectrum. Okay, so just to conclude, the idea was to try to average over all CFTs to arrive at something like pure 3D gravity, and that would only work if the CFT has a large gap and has all the nice properties that you would expect of a theory dual to pure gravity. And what we seem to bump into, whether you think about it on the space of all CFTs or in these particular examples, is that it's always exponentially unlikely with different scalings for a theory to be either holographic or pure gravity. All right, let me stop here. Sorry for going over time. Yeah. Yeah, that would be great. I don't know. Yeah. Well, in that vein, I think the even more interesting question is about this gap of central charges between CFT, this doubly exponential thing. Does that have a nice holographic interpret? And I would really love that, but yeah. Exactly. Yeah. Yeah. Yeah, we didn't talk about. I hope we do tomorrow, but yeah. No, that's very interesting, and I don't know if some of these weird exponential things have a connection to that. Those things. These are sort of subtle. Like it's not so easy to get something that goes like e to the minus n squared. This is like, and so it's more suppressed than the usual non-perturbative effect, like the subdominant geometry, but it's much bigger than these doubly non-perturbative effects. Interesting to understand how to make sense out of this, out of these gravitationally. I'm not sure. I'm not sure what to say in general. Again, this is a very special corner of theory space. Maybe it has nothing to do with gravity, but it's interesting that. Lunch.
Yeah, I think I think